We will now talk about uniformly convex spaces. So uniform convexity is a condition on the norm, so it tells you something about the geometry of the space. So if you look at the ball with the two norm in the plane, then it bulges uniformly in all directions, and if you look at the ball in the one norm, then it is something like this. It's a diamond, and if you look at it in the infinity norm, then of course you get a square. So these have flat portions on the boundary, whereas this one bulges uniformly. Uniform convexity in some sense analytically quantifies what is this uniform bulging in all directions. That is the thing. So we have the following definition. A norm-linear space is uniformly convex if for every epsilon positive there exists a delta positive, such that if x and y in V, so uniformly norm-linear space V, satisfy norm x less than or equal to 1, norm y less than or equal to 1, norm x minus y greater than epsilon, then norm x plus y by 2 is less than 1 minus delta. Okay, so this is the definition. So let us understand it briefly. So if you look what it's essentially, though we have said norm x less than or equal to 1, norm y less than or equal to 1, actually the important thing happens near on the boundary. Suppose I have 2 points on the boundary of the unit ball, so that means norm x equal to 1, norm y equal to 1, then it says that the midpoint must be away from the boundary in a uniform fashion, irrespective of the positions of the 2 points x and y. If you have x and y, as long as the relative distance is bigger than epsilon, then the midpoint should be sufficiently far away from the boundary. So that is what is given by this. So if you look at these points, the midpoint is also on the boundary, so it won't satisfy this condition on the L1 and L infinity cases, but in the L2 case you will see that it definitely satisfies. Okay, so this is what we mean by uniformly bulging in all directions. If you have 2 points on the boundary which are a certain distance apart, then irrespective of the position of the 2 points, the midpoint must be uniformly away from the boundary at a certain distance. Okay, so example, so ln1 and ln infinity, that means Rn with the norm 1 or norm infinity are not uniformly convex. In fact, they are not even strictly convex, which I introduced a little earlier. So example again, ln2 is uniformly convex. So let us take xy in ln2. This is the Rn with the 2 norm. Then this straightforward calculation. So norm of x plus y by 2 whole square in the 2 norm plus norm of x minus y by 2 whole square in the 2 norm is equal to 1/2 of norm x square 2 plus norm y square 2. This is called the parallelogram identity or the Apollonius theorem from plane geometry. So if you have, so this is x and y, then this will be x plus, if you take the midpoint here, then this will be x plus y by 2, this will be x minus y by 2 in length, and therefore this is the standard theorem in plane geometry known as Apollonius theorem, or this is also called the parallelogram law, because you can complete the parallelogram and says that half the diagonal, square on half the diagonal is equal to 1/2 of the sum of the squares on the other two sides. Okay, so that is this theorem. So this is straightforward checking, you can do it. So then if norm x is less than or equal to 1, norm y less than or equal to 1, and norm of x minus y is greater than epsilon, all in norm 2, then from this identity it follows that norm of x plus y by 2 whole square is less than 1 minus epsilon square by 4, which can be written as 1 minus delta the whole square, where delta is now given in a straightforward fashion by 1 minus square root of 1 minus epsilon square by 4. Okay, so once you have this, so you have uniform convexity. So we can also show ln in fact L2 for the same reason. In L2 also you have the same identity, so you can check it. So L2 is uniformly convex. LP is uniformly convex if 1 less than p less than infinity. So if in fact it is easy, we will see this later, if 2 less than p less than infinity, and then difficult if 1 less than p less than 2. So we will see this in when the time comes, when we do LP spaces. Okay, so you can, these spaces are all uniformly convex. Now the important theorem, why are we concerned about uniformly convex spaces? So theorem, this is the major theorem here. V uniformly convex Banach space, then V is reflexive. So you see the geometry of the norm tells you when the space is reflexive. Okay, so proof. So J V to V double star canonical embedding, okay, and to show J is onto. So that is to show JB equals B double star, where according to our notation B is the closed unit ball in V, B double star is the closed unit ball in V double star. Okay, now J is an isometry, so JB is closed, so sufficient to show JB is dense. Then JB will be JB is closed, so JB equals JB closure. JB closure is B double star, so JB will be equal to B double star. So this is what we want to show. We want to show that given any continuous linear functional on the dual space, namely a member of B double star which is in B double star, you can always approximate it by something from JB as much as you, as closely as you. So let phi belong to B double star, and we assume that norm phi equal to 1. Now if you prove it for norm phi equal to 1, then so to show there exists x in B, so to show for every epsilon positive there exists an x in B such that norm of phi minus jx is less than epsilon. So this is what, this is in V double star, of course. So this is what we want to show. So okay, so this is what we mean by dense. Now I have said for phi equal to 1, but then once you show it for phi equal to 1, then by scaling argument you can easily show it for any other phi with norm phi less than equal to 1. So norm phi less than equal to 1 follows by elementary scaling arguments. Namely, the theorem will be true for norm phi by norm phi, and then you have to do it. From there you can easily deduce it for any phi. Okay, so now, so we were going to assume that. Okay, so epsilon given. So let delta correspond to epsilon in the definition of uniform convexity. So you choose that particular delta. Now choose f in V star such that phi of f, so phi is a functional on V star, okay, so you choose phi of f, norm phi is 1, and therefore we can choose this to be bigger than 1 minus delta by 2, and norm f equal to 1. So norm f in V star will be 1, because what is norm of phi? It is the supremum of phi f or mod phi f if you like, but then phi f or phi f minus f together give you mod phi f. So supremum of the phi f over norm f equal to 1 will be equal to 1. So you can always find an f that is bigger than 1 minus delta by 2. So now you define u equals set of all xi in V double star such that mod xi minus phi acting on f is less than delta by 2. Okay, so f is a single point in the pre-space, so V double star we are working on. So this is u is weak star neighborhood of phi in V double star. Okay, so weak star open set and JB, but what do you know about JB? JB closure in weak star is equal to B double star. This we have already seen several and used in previous occasions also. Therefore, there exists an X in B such that norm such that Jx belongs to U, because every neighborhood must intersect JB, and therefore in the weak star section, in the weak star sense, and therefore there exists an X such that this is. So if norm Jx minus V is minus phi, sorry, is less than or equal to epsilon, we are through. We said strictly less than, but less than or equal to doesn't matter, so we are through. Okay, so assume this is not true. So norm Jx minus phi, let us assume, is strictly bigger than epsilon. Okay, that means what? That is phi does not belong to Jx plus epsilon B double star. B double star is the unit ball, epsilon B double star is the closed set of all vectors whose norm is less than or equal to epsilon. You are translating this ball by Jx. Phi does not belong to this means what? Norm of phi minus Jx must be bigger than, strictly bigger than epsilon, and that is the condition which we have put in here. Okay, so this. Now B double star is weak star compact because by the Banach-Kaloglu theorem, and therefore it is by, since the weak star topology is Hausdorff, implies B double star is weak star closed. So Jx, okay, I have written Jx to be consistent. Let me write J sub x plus epsilon B double star is just a translation of a closed set, so this is also weak star closed. So complement is weak star open. And phi belongs to this complement because we are assuming phi is not in that thing. Therefore, there exists a weak star open neighborhood u1 of phi such that u1 also is contained in jx plus epsilon b double star complement. Okay. Then again, u intersection u1 is weak star open, and so by the weak star density of JB in B double star, there exists x1 in u intersection u1 such that there exists x1 in B such that jx1 belongs to u intersection u1. Okay. So what do you mean by this? So mod of phi f minus fx is less than delta by 2 because jx, this is nothing but jx of f. So phi minus jx of f, jx belongs to u, and therefore you have jx belongs to u, and therefore phi x minus fx is less than delta by 2. jx1 is also in u, so phi f minus fx1 also is less than delta by 2. Okay. So add these two, from this you get that 2 times phi f is less than delta plus mod f of x plus x1, which is less than or equal to less than delta plus norm of x plus x1, because norm f is 1. Okay, so you have this. Now what is phi f? We have chosen it in such a way that is 2 minus delta is less than delta plus norm x plus x1, because we have chosen phi f in that fashion. Phi f is bigger than 1 minus delta by 2. Therefore, norm of x plus x1 by 2 is bigger than 1 minus delta. But x1 belongs to u1, that we haven't used that fact, and that implies that jx minus jx1 is bigger than epsilon, that is norm x minus x1 is bigger than epsilon. And we also know that norm x is less than or equal to 1, norm x1 is less than or equal to 1, because both of them are elements of B. So these two, and uniform convexity implies that norm of x plus x1 by 2 should be less than 1 minus delta, and that's a contradiction. Okay, so this is a contradiction, and therefore we have that norm of jx minus phi has to be less than or equal to epsilon, and therefore JB is dense in B double star, that is JB which is closed. So JB equals JB closure, which is equal to B double star. So J is on 2. So B is reflexive. Okay, so this proves the theorem completely. Okay, so now let us suppose xn converges to x in norm, then this implies that xn converges to x weakly. This we have seen, and we have also seen that the converse is not true. We have examples like En in L2 that goes to 0 weakly, but it cannot converge strongly. Okay, so xn converges to x in norm, implies by continuity of the norm, norm xn goes to norm x. And obviously this converse is also not true. You can have any set of vectors norm xn going to norm x, but that does not mean that xn should go to x. But if you combine these two relationships on the right hand side, if these two things happen, namely if you have weak convergence and the convergence of the norm, then it means convergence in the norm. Okay, so and provided you are in a uniformly convex space. So proposition. So V uniformly convex Banach space, and let xn converge weakly to x, and let norm xn converge to norm x. Then xn converges to x, that is norm of xn minus x goes to 0. Usually this will be difficult to prove. Proving weak convergence will be relatively easier, because you have to show that f of xn converges to f of x for every linear function, and also showing that the norm converges will also be relatively easier, and together these two in a uniformly convex Banach space tells you that you have norm convergence. So this is a very useful result. Okay, proof. So define yn equals, so nothing to prove, if x is 0, because norm xn goes to 0, that's exactly saying xn goes to 0 in norm. So nothing to prove if x is 0. So if x is not 0, so without loss of generality assume xn not 0. It's true for n sufficiently large, and therefore we can assume that it's for all of them. Okay, so now you define yn equals xn by norm xn, and y equals yn x by norm x. Now norm xn converges to norm x, and xn goes to x weakly. Together these two imply that yn goes to y weakly. This you can check. So all you have to do is take any linear functional, and you have to show that fyn goes to fy for every y in v star. This is what we have to show, and that is easy to show because you are given these two things. You can check it yourself. Okay. So we have that yn goes to y weakly, and now we have to show that yn goes to y in norm. Okay. So yn goes to y weakly, therefore 1, which is equal to norm y, is less than or equal to lim inf. So this implies that yn plus y by 2 also goes to y weakly, because yn goes to y weakly, yn plus y by 2 also goes to y weakly. Therefore lim inf of, as n goes to infinity, norm of yn plus y by 2, because we know if something goes weakly, then the limit and for norm of the limit is less than the lim inf. Now lim inf is less than or equal to lim sup n tending to infinity norm of yn plus y by 2, but norm of yn plus yn and y are all 1, and therefore by the triangle inequality this is always less than or equal to 1, and therefore the lim sup is also less than or equal to 1. Therefore we have that all equality is there throughout, and therefore you have that norm yn equal to norm y equal to 1, and norm of yn plus y by 2 converges to 1. That means for any delta positive, we have norm of yn plus y by 2 is bigger than 1 minus delta for all n greater than some capital N. But this means that norm of yn minus y has to be less than or equal to epsilon for all n greater or equal to n. Because if it were strictly bigger than epsilon, that will contradict the uniform convexity. You have norm yn equals norm y equal to 1, norm yn minus y bigger than epsilon, then you will have norm yn plus y by 2 has to be less than 1 minus delta, and that is not true. So delta corresponds to epsilon in definition of uniform convexity. Now you take delta corresponding to epsilon in uniform convexity, then norm yn plus y greater than 1 minus delta for all n bigger than or equal to n implies that norm yn minus y has to be less than or equal to epsilon, that is yn goes to y in norm, and this implies that xn goes to x in norm, and that completes the proof of this thing. So we will next look at applications of these results to the calculus of variations.